So thank you for inviting me to giving a presentation at your seminar series. And I'm going today to present to you a process-based radon flux map for Europe, the development, and just a short, small example of an application. All of this work is work I'm doing a bit on the sides of my usual work at the ICOS Carbon Portal, where I'm responsible for elaborated products, which are products based on ICOS data, to coordinate them and to host them and to help analyzing and visualizing and exploring them. But this work I'm doing together with Ingeborg Levin, this collaboration started a long time ago already, because we thought we would need a radon flux map for Europe. And I hope you don't mind if I switch off my camera now, because my computer is a bit shaky at this moment. Thank you. And I might not look into the camera anyway, because I have to look at the other screen. Thanks. Oops. Yeah. Okay, so the first question that we had was, of course, or is, of course, why do we need a radon flux map? So one reason would be obviously radiation protection, because radon is radioactive gas, it's naturally, but it causes lung cancer, for example. But this is not my field of work, so I'm not touching this. For me, it was more important to be able to use radon as a tracer for atmospheric transport. And as many of you might know, that radon is well suited for this, because it has a fairly homogeneous surface source. At least that's what one started out with in the beginning, to assume that it is really homogeneous. Radon is a decay product of uranium, and uranium is a component of all natural soils. So there is radon fluxes from soils everywhere. On the other hand, the ocean radon flux is orders of magnitude smaller. So you will always see a difference whether an air mass comes from the ocean or comes from a continental region. Furthermore, radon has a well-defined sink, which makes it also very useful in a model, because you can easily model this. You don't have to have chemical reactions. So this sink is radioactive decay with a half-life of 3.82 days, which is longer than the journal timescale. So you can handle it as a conservative tracer in the atmospheric boundary layer development during a day. And it is short enough to build up a vertical gradient in the troposphere. Due to these characteristics, as I said, it is often applied in atmospheric mixing studies. And there are examples like the evaluation of atmospheric transport model performance. This is what my reason behind it was to get started. And then there's also the radon tracer method, for example, with which you can estimate regional greenhouse gas emissions, making use of the correlation between greenhouse gas and radon concentration measurements, in particular during nighttime, when they accumulate in the shallow nocturnal boundary layer. But you also need information on the radon flux in order to estimate the greenhouse gas flux. So that's why we started with this development. So first, a few words on the processes of radon. So radon, if you can see my cursor would help. If not, then just imagine you are looking at the soil now, and radon is escaping from individual soil grains based on the amount of radon that is inside the soil. And then afterwards, radon is transported through the soils in the air-filled pore space. Radon cannot travel through the water-filled pore space, so really need to know where it can escape to the soil and then be exhaled from the soil into the atmosphere. So in this schematic, you see the individual soil grains and the water-filled pore space in blue and in white, the air-filled pore space. So this is the concept of the processes, but now we need to parameterize and model them for our radon flux map. So we start with the soil uranium content. As I mentioned, this is naturally occurring in every soil, so it's an important source information. And we also need information about the soil texture in order to know how much soil is there, to first estimate how much radon can escape from the individual soil grain. And in the next step, we need to parameterize the transport in the air-filled pore space. So we need to find out how much air-filled pore space we have. We need the soil moisture for this. And then we can parameterize the diffusivity, use a simple version of the diffusion equation, and then compute the radon flux. So that's the idea behind it. Now to some basic assumptions and basic equations that we are using. So first we have to calculate the production rate of radon in the soil. So as I said, this depends on the uranium content, so we need uranium information, and we assume that uranium and radium, which is the direct precursor of radon, are in equilibrium, so that we can just multiply the uranium content with a constant and then have the radium activity concentration in the soil. As I said, we also need information about the amount of soil. We need the soil biodensity, and we need the emanation coefficient, which describes the probability of the radon to escape from a soil grain. And this is depending on the soil type. For example, for sand, it is much lower than for clay. And as the radon can decay in this process, we also need the decay constant. So we have the production rate of radon. Next thing is we need to model the transport of radon. We assume that this is purely molecular diffusion, which determines the transport, and we neglect advective transport because this is really a lot smaller than the molecular diffusion. And doing so, we can use Fick's first law, which says that the radon flux in the soil is proportional to the concentration gradient in the soil, and this constant, or this effective diffusivity is then something we need to describe in the next step. It is not just this diffusivity is not just a function of the air-filled pore space, because the structure of the soil is very complicated. So that's why these parameterizations are a lot more complicated than just the amount of the air-filled pore space, but that's definitely part of it. And we need, for the air-filled pore space, we need the soil porosity and the soil moisture information. In the previous version of the map, and also in this version that we are just working on right now, we decided to, or we selected the Millington and Quirk parameterization, which so this decision was based on radon profile measurements that Ingeborg and her students had performed in Heidelberg and surroundings. So it seems that this one is able to represent this relation between the diffusivity and the soil porosity and soil moisture quite well. There are more complex parameterizations existing, but one limitation is, of course, that we need the input parameter for our model. So if we have then very complicated functions with very complicated parameters of the soil, which we don't know in the end, they would not help us a lot. That's why we decided to only test parameterizations which need soil porosity and soil moisture and nothing else, because it's difficult enough to get this type of information in the end for a map. And then assuming that at the boundary between the soil and the atmosphere, we have very low concentrations in the atmosphere compared to the soil, we can simplify the equation and this is then the way we compute the flux at the soil surface. So to illustrate this a bit more colorful and maybe a bit more intuitive, this shows a schematic diagram of the components and the workflow in the radon flux model. So I mentioned already the uranium content that we need. We take this from the Digital Atlas of Natural Radiation, where they have compiled a lot of real soil sample measurements from two different projects. One trying to really sample the natural soils in Europe on an equidistant grid as good as possible. And additionally, they also have data from a project where they are focusing more on agricultural soils. Together with information on the soil texture and the bulk density, which we get from the European Soil Database, both of those databases are hosted at the JRC. We can then compute the source term for our map. And then we need the soil moisture, and we use reanalysis data for the soil moisture. In this case, this is an example using the ERA5 land reanalysis. And we don't only need the soil moisture, we also need the porosity. We need the porosity that is used in this particular soil model, because this really has to fit, because we want to compute the air-filled pore space. So we use these two fields, and with the equations that I've just shown before, we compute the diffusivity, and combining this information, we get in the end radon flux. From the soil uranium, you see a very particular spatial pattern with low concentrations in Poland and in the northern part of Germany and in Denmark, and also here in Finland. And on the other hand, you have high values in some other places, and this clearly shows up in the radon flux in the ends. In particular, in this area where you have, in this particular month, you have a high diffusivity, and still you have very low fluxes because you have very low uranium concentration, whereas here where you also have a high diffusivity and you have a high uranium flux, you have a high radon flux.
Yes. I can't see your cursor, by the way.
Okay.
I don't know if others can.
And I don't know what to do about it.
That's fine. I think maybe just...
Okay, I can just stop using it. Okay, so the low values of the uranium content in Poland, for example, combined with the high diffusivity in Poland lead to small fluxes because there's just not enough, not much uranium. On the other hand, in the Iberian Peninsula, we have high uranium content, we have high diffusivity, and we have, in the end, high radon fluxes. This is what I wanted to show with my cursor. Thank you for notifying me. So this is a list of the input data sets, just in case you're interested in these details. So I already mentioned the uranium content. It is available on a 10 by 10 kilometer map for Europe, for political Europe, I have to say. We need the soil properties. They are on higher resolution in the 1 by 1 kilometer, on a 1 by 1 kilometer grid. And we are currently using two different reanalysis data sets, as I mentioned, the ERA5 land reanalysis, and also the latest version of the GeoDAS NOAA reanalysis. ERA land is on 0.1 degree grid. I think that's the highest resolution for a global model you can get at this moment for soil moisture, and GLDAS is like in previous versions on quarter of a degree. From the reanalysis, we use the soil moisture in different depths in the model. We use the soil temperature, which we need in the parameterizations. We use the soil porosity, and we also use the the air temperature to define frost days, because we assume that when you have ice-covered soil, then you have a reduction in the radon flux. This is not implemented in this current version that I will mainly focus on. We also have this limitation by water table depth. So if you have a very shallow water table, of course, you will only have a small amount of air-filled pore space, and then you have a reduced flux. We use this with a very high resolution. And then we also use a lithological map, because I mentioned already that the uranium content of the soil is only available for political Europe. But in the end, we want to use the map in a transport model, for example. So we need to cover geographical Europe. And therefore, we use the correlation between uranium content and lithology, which we define for political Europe to extrapolate the uranium content. This is not the best way to do it, but it's at the moment the only way we know of. And most of these data sets are kind of static, so they don't change with time, but the reanalysis, of course, are variable, and we are using monthly and daily resolution. For radon, it will not make sense to go to higher resolution, I would say. Yeah, so this is now a first result for this updated radon flux map. It's the monthly mean radon flux for January and July 2017 using the ERA5 land soil moisture. And we have averaged the soil moisture for a 40 centimeters deep layer, because we assume that this is the most important layer in the soil, which determines the transport of radon to the soil surface. And what you can see is what one would also expect, that in summer, I already showed this before, in summer you have high fluxes because you have low soil moisture and high diffusivity. But in winter, when you have generally much higher soil moisture, you have also reduced radon fluxes. So you would expect to see this strong journal cycle. And then just for comparison with the other reanalysis data set, on the left-hand side, you can now see the map for July 2017 based on GLDAS NOAA soil moisture. And yes, you see that there are similarities, but if you look into the details, there are also quite some differences between the two results. And focusing more on these differences, I will now show a time series of the soil moisture in the lower parts, in the lower two plots, and the radon flux in the upper two plots. These are time series for a grid cell in which stations close to Heidelberg are located. And there we had until now the best chance to have measurements for comparison. So in the lower, as I said, you see the soil moisture. On the left-hand side, monthly values for quite some years. So you can clearly see the seasonal cycle with high soil moisture in winter and low soil moisture in summer. And in particular, for example, in 2018, where we had this drought event, you see that the soil moisture is really low in both reanalysis data sets. On the right-hand side, you see daily soil moisture for the year 2017. What you can also see is that the soil moisture is a little bit lower in general in the GLDAS NOAA reanalysis compared to the ERA5 reanalysis, and also the amplitude of the seasonal cycle is higher in ERA5, not only the soil moisture itself. And this then directly translates into the seasonal cycle or the seasonal variations of the radon flux in the upper graph, where you can see that we have lower radon fluxes using ERA5 and systematically higher using GLDAS NOAA, but we have a stronger seasonality in ERA5. And yes, on the right-hand side, you see it on a daily scale. And there you see that, yes, there are, again, systematic differences between the two data sets. We have, what is shown here, I forgot to mention, sorry, is a mean for a 0.5 by 0.5 degree region, and also the heterogeneity, which is displayed by this band around the mean value. Just to show you that there is quite some variability in this on this scale. So next, for this particular station, we can compare two observations. There are some observations available, but unfortunately not at the same site. The sites are in the same grid cell of the model, but not really close by each other. So in the lower part, you see now also the observations at the station Grenzhof. The soil moisture that I have included in this comparison is for 25 to 30 centimeters depth. And what you can see is that the observations are systematically lower than the real analysis, but also the porosity is systematically lower. And I mentioned before, it is important to look at the air-filled pore space. So that's why I will now show, instead of the soil moisture itself, I will show the air-filled pore space. But even though we take now into account that we have a different porosity, still the values are systematically different between the observations and the reanalysis. In the radon flux plot, you can now also see radon fluxes. They are, yeah, it's kind of a climatology. They have been measured in the vicinity of Heidelberg at the station M5 long before we started with this map. So we compiled them into a climatology. That's why it's the same for every year. It's just in order to show what we would expect, what kind of seasonal behavior we would expect to see. Yes, they are a bit higher than the model results, but at least the amplitude in the ERA5 derived radon flux is of similar size. When we now look at the soil moisture on the daily time scale, yeah, so we are covering or we can represent with the models kind of the temporal behavior of the soil moisture on a monthly and on a journal time scale. But with the overall value, we do have a bias, which will create problems in the end. Yeah, so that's it, what we have in terms of comparison to observations. And
Ute, can I ask a question?
Yes, sure.
So how are those radon flux measurements made?
I'm really not an expert in measurements, but they are using this kind of box you put on the ground, and then you let the radon get into this box, and then you measure the radon decay again. But
okay, so it's like a chamber type.
Yeah, chamber. Yes, chamber is the word. Thank you.
Okay, so very small scale then compared to your model.
Yes, it's very small scale, and that's overall the problem of the validation, which I will touch upon later in my talk. So we really have a problem to validate the flux map. We always have, and currently it's not yet improving. We hope it will in the future. Yes, so that's it for the comparison. And now next is the comparison to the previous version. because you might have used the previous version, which was released in 2015 in an ACP paper. And so what has changed and has been updated since then is that we use this uranium map, which now also includes samples from agricultural soils, which in the end results in a higher, on average, higher radon source of 30%, which is quite something. The ERA reanalysis have been updated from ERA interim to ERA 5. The model is still more or less the same. There were some changes, but the most important change is that the spatial resolution is increased quite substantially. And with 0.1 degree is now much more what we need for our work. And also GLDAS NOAA has been updated. In the new version, the soil moisture is systematically higher, and but in some regions, the seasonal cycle amplitude is reduced and looks a bit awkward. So in this lower panel, you see the radon fluxes for the same station that I just showed before. And in red and blue are again the current versions of the radon flux, and in orange and light blue are the previous versions. So in the first version, we tended to favor the GLDAS NOAA based radon flux because it seemed that at this station and also at some other stations, we didn't have very many stations, but nevertheless, the amplitude and the level of the radon flux seems to fit better to observations. But now this has changed completely, and GLDAS NOAA is no longer our favorite model, and maybe we would then concentrate in the future on ERA 5 land, which is different than the version before, but still has a similar level of soil moisture and also a similar amplitude of the seasonal cycle. This is now a comparison of the 4 different maps, so the 2 versions and the 2 different reanalysis data sets, more for the whole of Europe, the European land surface. On the left-hand side, you see, on the far left, you see the new version, the frequency distribution for the new version, and in the middle you see from the previous release in 2015. So you see that for ERA, the distribution has changed. It has a broader distribution now, the flux, which is partly due to changes in the soil moisture, but also partly due to the new uranium flux that we are using, which has higher values. The mean value is slightly higher, but it's not significantly different. For GLDAS NOAA, the frequency distribution looks a bit unexpected. The mean value is still similar. On the lower right, you see now the monthly mean fluxes to see the seasonal cycle for the European continent. And again, you see that we have this seasonal cycle, and now the amplitude of the blue and the red curve are more similar, but still the red curve is favoring, is giving higher radon fluxes. So, but we don't want to only compare this to our previous maps, but also to other existing radon flux maps. Unfortunately, not very many radon flux maps exist. So on the right-hand side in these frequency distributions, in the upper panel, you see the results from Lopez Coto. He was also using an ERA reanalysis, the ERA 40. And it is also based on a similar approach like we are using, but he has a real diffusion model, which he then calculates into It calculates until it is stable and then infers the radon flux. However, he has much lower fluxes, but that is probably mainly due to his estimate of the emanation coefficient, which is systematically lower than the one that we are using, or the ones that we are using. In the lower panel, you see the lower right panel, you see the fluxes based on or provided by Cecvari. These are based on gamma dose rate observations. So they use gamma dose rate observations and co-located radon flux measurements to infer if they are correlated, then to infer the fluxes from gamma dose rate everywhere in the European domain. They get similar values like we get, and also the distribution looks similar. So now the question that is our most important question since we started working on this. So how to validate these radon flux maps? First point is that we saw that the differences in the soil moisture directly translate into differences in the radon flux. So a good thing would be to start with the soil moisture validation, but this has some limitations. Like many measurements, they are not representative for larger areas. So you will have the problem to compare real point measurements to a map grid cell, which is in our case 1 by 1 degree, 0.1 by 0.1 degree. So that is a problem in itself, and is not only true for soil moisture, but soil moisture is particularly heterogeneous across the soils. Another problem that we face is that the quality control of measurements, of soil moisture measurements, can be an issue. So we have looked at soil moisture measurements from ICOS ecosystem stations, for example. They all measure soil moisture at several places around the greenhouse gas measurement tower. But unfortunately, the quality control is not fully implemented yet. So it's a bit difficult sometimes to interpret the measurements. We also looked at the International Soil Moisture Network. They have a huge amount of stations and networks of stations. Again, it can be a bit complicated with the quality control. But on the other hand, we anyway have to restrict it to a subset of these measurements, because we need to have the information for deeper levels in the soil, like 20, 30, 40 centimeters, and not just the uppermost level that is also used for the validation of satellites retrieved soil moisture, which, for example, would also be a potential candidate for the validation of the soil moisture, but unfortunately is only the first 1-2 centimeters, which is not useful, really useful for us. Not in the end, of course. There are attempts for sure to validate the reanalysis data sets. And the result of these studies is that the absolute value of soil moisture is not well represented, so that's difficult. The temporal variability, on the other hand, is well represented. Yes, that seems to be true for ERA 5 from what we see, but we need the absolute values. We need to validate the absolute values of the soil moisture. That's one of our main problems currently. The other strategy is, of course, to validate the final radon flux. Again, we face the same problem, that the measurements are not necessarily representative for the map. And up to now, we have the problem that only very, very few campaign measurement datasets exist. So we don't get information about the seasonal evolution of the flux. We just have measurements here and there. And we often don't have co-located measurements of soil moisture and soil properties, which we would also need for the interpretation. Another option would be to have a top-down validation of the radon flux by using the radon activity concentration measurements in the atmosphere. That could be kind of measurement-based, where one uses the vertical gradients in the radon concentration at tall towers to estimate from the accumulation in the shallow nocturnal boundary layer the concentration, the flux close to the tower. Another possibility would be to use atmospheric transport model simulations to relate the radon fluxes and the atmospheric radon concentration, and then see if we can infer some characteristics of the radon fluxes. But this is, of course, the kind of circle, because we started out with using radon to evaluate the transport in the transport models. And yeah, that's something we need to disentangle and make clever choices and clever constraints when we can use it for the validation of the flux and when we can use it for the transport validation. So luckily, there's now the Trace Radon project. The objectives of this project are traceable measurements of radon activity concentration. That's nice, in particular for the ICOS stations, of course, good to have, or for other atmospheric stations as well, for sure. Traceable measurements of the radon flux, which is also really good for us for this study. And we also have to provide a validation of existing radon flux models and inventories, and also use this then for radiation protection issues. This combines two communities, the greenhouse gas monitoring and the radiological monitoring. So the idea is really perfectly suited to what we are doing. That's why we are partners, or at least I'm partner, and Ingeborg is collaborator in this project. But on the other hand, we can already now foresee that we will not get years of flux measurements. We will just get a few months here and there in total for campaigns. So it will help us to validate the assumptions and the real model, so the parameterizations in the model. But it will be difficult to use this to validate the full map. So there's potential for the future. So now to the application of the radon flux map, or potential application of the radon flux map. So one could use it, and that was what we started with, to evaluate atmospheric transport model performance. And I will show some results from the STILT transport model. So we compare the model, the atmospheric transport model results with observations of the radon activity concentrations at stations, for example, in the ICOS network. The radon tracer method would also be a good application for the radon flux map, because it uses this correlation between greenhouse gas and radon concentration measurements, together with radon flux estimates in the footprint of the station to derive estimates of greenhouse gas emissions. But as we can imagine, biases in the radon flux directly impact the estimation of the greenhouse gas flux. And we currently have a paper in the discussion phase in ACPD. So I will now concentrate more on the comparison of the model results with measurements. In principle, we have radon measurements in the ICOS station network available. It is a recommended measurement component at ICOS sites. It is not mandatory, so not all stations have and will have radon measurements available. So on the right, you see a list of currently 14 stations which have set up radon measurements or are setting up their measurements. So they are not yet freely available as real product in the ICOS Carbon portal. They use different monitor types. So on the left-hand side, you see the map with all ICOS stations, with all labeled ICOS stations in red. And the yellow ones and the orange ones are the ones where we have already radon measurements. They use, as I said, different monitor types. Some use the ANSTO, which really measures radon gas, and some use measurement devices that measure the progeny, the radon progeny, and are less direct and needs calibration, or they need to be brought to the same scale or calibration. I will show examples for the Karlsruhe tall tower kit, which is shown here with this orange yellow symbol because it has progeny and ANSTO measurements there. So this is now the radon measurements at the tall tower in Karlsruhe. The polonium, so the radon progeny, is measured using the Heidelberg Radon Monitor. And these measurements are conducted at 200, 100, and 30 meter inlet height. And then there's an additional ANSTO measurement at the lowest level of the tower at 30 meters height. There's a calibration difference between the different types of monitors, and the progeny measurement has additional problems or issues because there is aerosol loss in the intake line, which is important for long intake lines and needs to be taken into account. And then there's also a disequilibrium between polonium and radon in the lower levels. But all of this has been corrected and compared to the ANSTO measurements, which were conducted at the same time for some time periods. And all these measurements are now available for our study here. So this is now an example of summer and winter episodes of atmospheric radon from the observations in Karlsruhe at the tower at 100 meters height. In the upper panel, you see summer months, an episode in July 2017. In black, the observations, and in blue, the stilled model results. And in the lower part, you see an episode in winter in November 2017. Same color scale. So the radon flux map that we were using in these simulations is still the old radon flux map. And as we didn't have radon fluxes for 2017, we constructed climatology and used the same fluxes every year. So you're probably anyway familiar with radon and its variabilities, and that it is varying on different timescales. And in particular in summer, you can very well see the Journo cycle, which is caused by the Journo cycle and the vertical mixing processes in the boundary layer. And it is not influenced by the radon fluxes as such, because we assume that the radon flux is at least on hourly timescales, or in the Journo cycle, not varying so much. But clearly, the amplitude of the Journo cycle scales with the radon flux around the tower. In the winter episode, you can see the variations more prominently on the synoptic scale, which are caused by variations in the air mass origin, where we have this continental versus marine air difference, where there's no radon flux over the ocean. And it is also caused by regional differences, of course, in the radon flux, depending on where the wind comes from or where the air comes from, whether there's more or less radon flux. Additional to this, what you can kind of guessed from the two winter and summer episode, there's also a seasonal cycle, which is caused by the seasonal variations in the atmospheric transport patterns, but also in the seasonal cycle of the radon flux, because as you saw before, we have small fluxes in winter and early spring because of the low soil moisture, the high soil moisture, and low and high fluxes because of the low soil moisture in summer. So here it already gets complicated to disentangle these two components. In Karlsruhe, we have the measurements at the 3 levels. And here I compare the mean journal cycle for August 2018 from the measurements in the grayish colors and the model results in the bluish colors. So in model and reality, you see that after sunset, the radon concentration increases, in particular in the lowest level close to the surface, because the nocturnal boundary layer is quite shallow in the end, and the radon that is emanating from the soil is just piling up in this boundary layer. You also see this in the upper more layers, because usually the boundary layer height is a bit above the tower. You see a similar structure in the model, but you see also that there is a time shift. In particular, in the morning when the boundary layer starts to break off, because after sunset, after sunrise, there's more turbulence, and then you're mixing the radon better up to the highermost levels, and there you see a shift between when the mixing starts in reality and in the model. So this could partly be caused by the problem or the fact that we have only 3-hourly metrology to drive the model, and even though we interpolate and also compute the turbulence on a shorter time step, we still have, of course, an effect of this 3-hourly metrology. So this is clearly one disadvantage of the model, or one problem of the model. Yes, what you can also see is that during nighttime we have a stronger vertical gradient. So probably the vertical mixing is too strong is too weak during nighttime. So the boundary layer is too shallow, and there's not enough mixing. On the other hand, when you look at the daytime values between, let's say, 11 and 4 in the afternoon, you see that in the measurements you still have a vertical gradient, which you don't see in the model results. So during daytime, the vertical mixing in the model might be too strong compared to reality. So there are many things to look at, but as I mentioned before, we have to disentangle also the influence of the radon flux from the influence of the transport properties. Here we see this bias, and this overall bias in the concentration in the model concentration, between the model concentration and the observations. So maybe that could be an indication that fluxes are too low in the surroundings of the station, because at the station itself, the fluxes are probably not too low because we have these very strong gradients during nighttime, and this very high values close to the surface. So this brings me to my conclusions and the outlook to the near future. So we have now these new radon flux maps with higher temporal and also partly spatial resolution. Now in the new version, the soil moisture models show better overall agreement with each other. The validation of the soil moisture as I mentioned, is currently ongoing, but still a bit inconclusive because of the missing reliable observations. We will look for more observations to see if we can infer some reasons why there would be a difference. The validation of the radon flux itself simply lacks systematic observations at representative sites. And it definitely also needs to include measurements of soil properties and soil moisture, which was not the case before, but hopefully will be in trace radon, at least as a start. The uncertainty of the mean European radon flux is on the order of 25 to 30%, but that's the mean flux. On the regional scale, this is much more uncertain, and the uncertainty is a factor of 2 larger at least. So using radon as a quantitative tracer for atmospheric transports, either for the evaluation of transport modes or for application of the radon transfer map, is associated with similar uncertainties. So our request would be that one should start systematic radon flux measurements around the atmospheric stations in ICOS, but also in other networks. And with this, I would like to thank you for your attention, and I'm happy to take questions.
Fantastic. Thanks, Ute. Right. Do we have any questions? I'm sure Aoife would encourage you all to turn on your cameras if you can. Joe, go for it.
Hi, thanks for that. That was really interesting. I was just wondering about the results you showed, the comparison with still the diurnal cycle at the end there. I was wondering if you were able to look at the other gases that they measured at the site as well, maybe things like, I don't know, like methane and N2O, and see whether do they show the same sort of pattern where the, you know, if you model them, that the model is mixing too strong in the day and too weak during the night.
Yes, so we do see a similar pattern also in those gases. Yes, as far as we could look at it, we have been looking at some of them, but yeah, it seems to indicate that this goes into the same direction.
Great, thanks. Andrew?
Can you hear me?
Yes.
Yep.
Okay. Interesting talk. I'm based at University of Reading, and I'm doing some work to evaluate a new turbulence scheme in NAME, looking at a varying scheme for the free tropospheric turbulence. In the model that you're using, the Stilt transport model, how does it treat the free tropospheric turbulence? Is it set to a constant value or a fixed value?
Good question. I have to admit that I don't remember it from the top of my head how exactly this was done.
Yeah, I mean, I've just been looking at the website and I can't find any documentation for the model that we're using. The only reason why I bring it up is because some of my initial results looking at this new turbulence scheme in NAME sort of suggests that there could be some effect, especially at night time, that you get some extra ventilation of the radon through the boundary layer, reducing concentrations near the surface. So is that something that could explain some of your results, observations?
It would probably, at least, yeah, what we see is that we don't have enough enough mixing, and in that sense it could be, yes, we don't have measurements higher up, so it's probably really the lower part of the boundary layer.
Okay.
I think we should also, for further evaluation, we should also look to the meteorological parameters that are measured at the tower. That's something we did not yet do.
Right. Okay.
And with at all the towers in ICOS, we do have meteorology available. So it would be a potential to look at that as well.
Okay. Thank you.
Any other questions? I have. So I'm thinking about the uncertainty in this map, as I guess I've thought about a bit from our earlier conversations, and I'm just wondering how realistic it is to get, or how far away are we from getting a kind of robust uncertainty estimate with this kind of map? I'm just thinking about, do we even know where the key uncertainties are? Do we know that they're in the inputs, like the soil water levels, or are they in the parameterizations? Do we even know where to look?
Yeah, that's of course a good question, and difficult to find out which would be more important. But so the approach that we are using and the parameterizations that we are using, that's the part that we could evaluate with some existing measurements close to Heidelberg, so measurements that were conducted by Ingeborg and her students. And we hope to get closer to evaluating those in the Trace Radon project, when we will have radon flux and soil moisture and porosity and all the information we need at one site, and with time resolution of soil moisture. So this would then help us at least to better evaluate this component. But from the analysis of the different components, it's for us, it's clear that it is the soil moisture which is the most important, uncertainty. In particular, as the level of the soil moisture, so the overall soil moisture, is the most uncertain.
Okay.
So I'm quite confident that the temporal variability is well represented, and yes, that's within the uncertainty we can anyway get, but the level of the soil moisture, that's the most important problem we see, and the most important uncertainty. There are uncertainties in all the other components as well, but this one seems to be the driving the uncertainty.
That's really interesting, because it would suggest that the uncertainty in day-to-day variations should be smaller than the uncertainty in the absolute levels. Mm-hmm. Is that fair?
Mm-hmm.
Yeah.
Yeah, that's what I would expect. But again, we don't have radon flux measurements on the daily time scale. So that's why we are looking forward to the first measurement campaigns in Trace Radon, to see if we can reproduce this with our model.
Yeah, fantastic. It would be great to see those.
For these measurement campaigns, we can just use the measured soil moisture as input parameter to our parameterizations, and then we can evaluate directly what the fluxes should look like, and what the fluxes look, and how the parameterization performs.
Yeah. I can see Alistair's got his hand up.
Thank you. Great talk, Ute. Yeah, just to see how this work has evolved since INGOS and things. It's very, very complicated ultimately. So my question really is, when they're doing these campaigns, are they going to really investigate the non-uniformity of the emissions in a small grid box? So basically in a 1 kilometer box, are they going to look at that at all? Because you just measure at one point and you might get a very unusual answer there, just because the rock formation is not quite what they think it is.
Mm-hmm. Yes, that's one of the limitations. Initially, we had the idea that there should be at least 2 automated chambers running measurements in these campaigns at each station, so that this is for sure not covering the full heterogeneity, but still it gives you an idea of how heterogeneous this is, but not so sure we will have two. And we will have soil moisture at different locations. But there are so many practical restrictions with these measurements, like it should be in a fenced area. There are so many, it should have no longer than 30 meters power supply, and so on and so forth. There are trees, because at the same time there will also be gamma dose rates measurements in order to also come up with a similar map based on the Jaguari approach. And they don't want to have trees close by. So it seems to be complicated from what I heard in the discussions. So ideally, we would want to have several measurement devices deployed in one campaign, but yeah, restrictions.
Yeah,
because yes, at least it would be good to have an idea on the heterogeneity of the soil itself. So the soil can be very heterogeneous, I would expect. And yeah, it's not really necessarily representative what is measured.
So I mean, it sounds from all the complications that we're quite some distance away from quantifying whether atmospheric transport models are doing a good job or not using radon.
Yes, I think you can. You have to look at specific aspects of it. I think you cannot overall just use the time series and then there you go. You need to restrict it to specific questions, to specific episodes. You need to have more information than just the radon. Yes. And yeah, it turns out to be more complicated than we initially assumed, because previously everyone was using just one constant value for the flux and everyone was happy. Now we started looking into this already years ago, but now we are less happy than before, because we see that it's not this homogeneous source that we always thought. It is still homogeneous, but not as homogeneous.
Yeah. Has anyone done I mean, this is quite a wild idea, but actually done an inversion on the measurements that are made now using these ancestors?
Not yet. I think that was one of my ideas to do so, but at the moment I think it is the data set is a bit too limited. We don't have very long time series, and I think you should cover the same time period with several stations would be ideal. But I think that's one of the next steps. As soon as you have a network of ANSTOs and well-calibrated Heidelberg radon monitors, it would be a good idea. I have read a paper, which is already a while ago, where someone tried this for China or some other country, and yeah, in the end, wasn't really conclusive. But
no, I suspect the soil moisture aspect and the variability of that in time will be causing some complications to that inverse system.
Yeah, that's again one of the complications. Yes.
Thank you.
So Angelina has a hand up, and I think we'll have to make this the last question, not least because I've got to go and teach in a second. Angelina, go ahead.
Yes. So my question is, if it's really hard to do the soil flux measurements, would it be easier to do more, like have more sites that have gradient measurements of radon?
That's a good question, which should probably better be directed to Ingeborg, who's more the measurement person than me. We haven't explored or exploited the profile measurements enough, I think. But currently we don't have stations except for Karlsruhe available for these.
I think Cabao has
as well, yes, but that's only partly part of ICOS. That's why I don't have everything. Yeah, but they have two levels. Yes, those are both. And briefly looked at the first data set from Cabao, and we see similar issues in Cabao, but less pronounced than in Karlsruhe. But Karlsruhe is also more continental, while Cabao is closer to the sea and has stronger turbulence.
Okay, fantastic. Well, thanks very much, Ute. I think I'm sure you're going to be hearing a lot more from a lot of the people on the call here today. I mean, we're going to be starting generating some time series, model time series to compare against the observations we have in the UK, and yeah, it'd be great to look at your new version of your map and see how it does. So
yes, and I would be interesting to see how it does in your simulations for sure. Yes.
Definitely.
So it should be a first version should be available soon for testing, just for testing.
Fantastic. That would be great.
We ought to compare the soil moistures in the versus.
Yeah.
Just to throw that in. Sorry, Matt. I know you want to close now. Sorry.
Yes, but that would of course be also interesting for us to see whether there are better soil models than what we get from the reanalysis, which are not really made for soil moisture. So it's a meteorological analysis which has been run on higher resolution to have the land covered better, but it's still, the land is kind of a bucket where you can drop everything in order to get the 2 meter temperature, right? So they are not really designed for the soil. They are designed for being part of a meteorological model. Yeah. So that could also be helpful.
Yeah. Okay. Well, thanks very much, Ute. It was a really interesting talk and really interesting discussion. So yeah, thanks very much. All right, guys, we will see you all soon.